So write down the heading as chapter 4. Chapter 4, Newton's laws of motion. So online, are you able to hear me?
Yes, sir.
Get started. Chapter 4 is Newton's laws of motion. So, what were the chapters that we were dealing with? If you see from the beginning, what were the chapters we were really concentrating upon? First is we saw what are units and missions. After that, we started focusing on chapters where we were concerned about the motion of objects. Right? So, what is the name of the third chapter? Motion in a straight line. So, what was the chapter of? So, what did we mainly discuss in motion? Concepts inside. But if you see the main context of what motion in the straight line spoke about is, you are mainly concerned about calculating certain parameters which are related, which are associated with whether the object is at rest or in motion. Means we are talking about the related concepts happening with respect to time. So what are all the parameters that are changing with respect to time? Suppose the object has started from origin. So as it starts moving in a straight line, but that's the name of the chapter. Straight line. As it starts moving in a straight line, what happened? Its position changed with respect to time. So in the position, you would associate it to scalar quantity, what it as distance. If you would associate it with the vector quantity, you got it as displacement. Right? Yes, so you spoke about the rate of change of distance, you called it as speed. On the counterpart, you call the rate of change of velocity, you call it as velocity. So similarly, if you call the change of the rate of change of velocity, you call it as acceleration, right? So these were the main concepts we were discussing there, right? So I have this in your mind there, we call it as motion in a state. When we saw the chapter name, the motion in a plane. So plane generally refers to two dimensions. So what if we discuss in motion in a plane? We are concerned about the change in position of the object with respect to the x and the y axis, or it can be any other axis also. Right? Mainly, we are concerned about an object which is not confined to the motion being along one dimension. Rather, we started looking at the motion with respect to two dimensions. Those two dimensions will either be x axis, y axis, or x axis, z axis, or y axis and z axis. Out of all the three, only a permutation and combination of two are taken at a time. We call it as a plane. Right? So in the chapter, what were we dealing about? We mainly started discussing about how to represent the physical quantities as vectors. In the previous chapter, that is motion in the straight line, we tried to classify the elements of scalars and vectors, but we never learned the method of how to represent the quantities as vector quantities, or how do you notate, how do you give a symbol to them so that it gives universal answer. Right? That is what we mainly concentrated in the whole chapter, which we call it as vector algebra. So once we did the vector algebra part, then we started focusing on a concept called as projective. Yeah,
Sir, your voice is very low, sir.
my voice is
Very low.
very low. Okay.
Now is it better?
Yes, sir.
Speak. Now is it better?
Yes, sir.
So listen. So what were we discussing? We were discussing about the concepts of projectile motion, where we saw what will happen to an object projected at a certain angle with respect to either horizontal or vertical. See, when it comes to your textbook concepts, we mainly discuss only about the horizontal. We never concentrated on what happens when it is projected vertically. That's not a very big deal. With respect to horizontal, it's theta. With respect to vertical, it is 90 degrees. That is only difference. Okay. So apart from that, we also try to understand a concept called as uniform circular motion. Right. Then we discussed the outline of the last concept, that is called as relative velocity. Right. So when we were discussing about the motion in one dimension or motion in two dimensions, we were not concerned about one point. That is, what was the cause behind that particular motion we even have? We never even questioned. They told us that there is an object, it is moving from one point to another. Calculate this value and give it to me. We did it and gave it to us. Right? They asked you if this is the change taking place with respect to displacement, calculate the velocity. Whether you're asking about average velocity or instantaneous velocity, we still try to do it according to the equations, the mathematical equations we had in our hand and gave it. Right? Now, the time is to question why is the motion even happening? Right. So if you see the last parameter that is associated with motion of an object, it is acceleration. So first we speak about displacement or distance, then we speak about velocity or speed, and the third important parameter we speak about is called as acceleration. So acceleration has something to do with the cause, which is making the object move. So based on you answering the question of whether you're going to study about the motion with cause or motion without cause, the physics itself is broken into two main branches. I repeat it. You see, if you deal with the study of motion with cause and motion without a cause. Okay, these are the two possibilities. So if there is an object that is moving, then somebody should have moved. You don't know who that somebody is. Okay, that somebody when they are trying to move, they are trying to put in some effort. So we need to give a name to that effort in terms of physics. Right. So if you see, motion without cause was what we discussed in the third and the fourth chapter. And that branch of physics was classified as kinematics. So the branch of physics where you're concerned only about the motion, but you're not concerned about the cause is called as kinematics. Whereas, if I give you a branch where you're concerned about the motion as well as the cause, then that branch of physics is called as dynamics. And here comes an important belief in this chapter, that is, Newton's laws of motion falls under the branch of physics called as dynamics. Here. So repeat, Newton's laws of motion falls under the branch of physics called as dynamics, because in this chapter we will be discussing about motion as well. At the same point, we will start asking a question of who caused this object to move. Now, if at all I have seen, let's say I have this water bottle. Okay, I'm holding it in my hand. Is it right? So I'm holding it, and if at all I'm able to keep my hand stationary, I can say that this water bottle, in terms of physics, is at rest. In a layman point of view, you can say it is stationary. It is just at its position. Now, if I start making this legs, what did I do? If you observe, I repeat it, listen to this carefully. If I start moving it in this way, if you observe, the platform, that is my hand with which this bottle was in contact, also was moving. Right. So, can I say that this object had motion? That is a relative term. Because I will say this object had motion with respect to ground, yes. Because ground is at rest, whereas my hand was moving. But if I ask the question, say, is this bottle having motion with respect to my hand when it is moving like this? Answer is no, because as the similar to the way the bottle had motion is the case with respect to my hand also. So both had the same kind of motion because they were in contact with each other. So you're able to understand what I'm trying to say here. Motion is also a relative term. But if I keep my hand stationary and I take the help, see what did I do in the previous case? I just moved the platform on which this was resting. But here what I'm doing is I'm taking the help of my other hand. I'll keep my hand stationary, my left hand stationary, and I'll start moving this bottle. Is this bottle having motion with respect to my left hand? Yes, it is. And why is it happening? To cause the motion to this object. The answer to that is something I did with my right hand. What did I do? I held it here, right? I held it here and I pulled it in this direction. So if you see from this side, you call it as pulling. If you see from this side, it's called as pushing. Now the lead comes. In physics, if you apply something called as a pulling or a pushing effect, you call that term as force. That's what you learned in your lower grade. So when somebody asks you what is force, in the textbook it is given as a push or a pull, which is acting on an object. But are you able to visualize it? So suppose you go to a door, like say you go to a hotel, okay, or a restaurant, where you're trying to enter. Generally, if you see, the doors will be having a handle, and they would have written push or pull. So if you see both the sides, they would have not written it as push. Right? Nobody will do that. So one side, if they write it as push. So what you do while you're entering, if you're asked to push like this and enter, so the person on the other side, when they're trying to come out, what will they do? They will try to pull and come out. So that the door is having the efficiency. Are you able to understand? So actually what you're doing, That is push or pull is a layman point of view for everybody to understand. Nobody will say apply force in this direction. Have you ever seen any poster like that? They will not do it. So push and pull is a simple term for us to understand. So you just apply a force against you, you call it as push. A force which is applied towards you, you call it as pull. And for any object to have motion in this object, motion in this world, I told you, right? Motion plus cause is called as dynamics. So who is the cause which is making the object move? In every scenario, it is the force which is responsible for the motion of an object. Is the point clear? Is it getting registered? So if you see Newton's law of motion, we are mainly concerned about discussing a parameter called as force. And how did I define this force? As force is basically a push or pull. Right? So you generally don't apply anything like push or pull on an object without having any end objective. You just generally don't keep doing it. So what is the objective of you applying this push or pull? It is to ensure that the object has push. So push or pull applied on an object to do what? To make it move is called as force. Is the point here? Make a note of this. Right. Is this point clear? Okay. Now comes another important issue. So when you talk about the motion of an object, so the motion of an object can either be restricted to translated motion, like how I showed. Okay. Suppose you see this bottle, keeping my left hand stationary, if I move it, this kind of a motion is called as translatory motion because it is moving in a straight line path. Whereas I can talk about the motion of this cap also. So if I want to drink water from this, what am I supposed to do? I will keep my hand like this. I will rotate it, right? When I'm rotating it, what I'm doing is, my finger is there here. When I try to rotate in this direction, I'm able to experience some resistance that is occurring. So the name of that resistance, because there is, see if I apply oil on this, okay, oil or grease on this and I try to open it, maybe I'll not be able to do this because my hand will have a slipping effect. But here, something is actually helping me to open it. What is it? So it is basically friction. So I'm applying the force in this direction, right? So I cannot do it with single finger. I need the help of another finger also, right? So if I apply a force in this direction, what is happening is, I'm experiencing a resistive force in this direction. Similarly, when this finger is trying to pull the object towards me, I'm experiencing a resistive force in the other direction. So the friction, which is actually coming to picture, needs to be overcome by my fingers so that I am able to make this object move. Here also I'm saying the object has moved, this cap has moved, but the difference is, when you talk about the bottle had translatory motion, but this cap had rotation motion. It's not circular motion. Don't get confused. There is a difference between circular motion and rotation motion. I'll come to that. For example, if you look at this fan, right, you say this fan has rotation motion. You do not say fan has circular motion. If I take a small piece of clay, okay, if I take a small piece of clay and stick it at the top of the bottle, then if I start revolving it like this, then I will say that the cap had rotational motion, but the clay which got stuck here had circular motion, because circular motions are mostly defined only for particles, whereas rotation motion is defined for objects. So cap is an object. So you say here you have rotation motion. The reason why I mentioned about this is the name of the chapter suggests laws of motion. I told you motion plus cause, but I didn't tell you which motion I'm trying to talk about. So motion itself is basically classified into two types. What are they? One is called as translatory, and the other important one is rotational motion. And the third type of motion is also there, which is called as vibrational. If you talk about a spring, For example, you have a ballpoint pen. When you click it, right? You have a ballpoint pen which has a clicking effect. So how is it actually working? Because of the spring that is present inside, right? So if suppose you keep that ballpoint pen in the reverse, you press it like this, but you remove your hand. What can you observe? It starts jumping. So had there been an allowance, it will start vibrating, right? So you talk about vibrational motion for elastic objects. So what are they? Three types of motion. One is translatory, second is rotational, third is vibratory motion, right? So for each motion, the cause will vary. So why I'm stressing it here is because when you talk about force, force is responsible for translatory motion of an object. So in this whole world, I repeat it, in this whole world, if you have an object being put in a straight line motion, you should apply only force. I repeat it, force is responsible for translating motion. So if you see any object which is moving in a straight line path, and if someone asks you, who is the cause behind the object to move in a straight line path, your answer should be a one word answer which states force. Because force is responsible for translatory motion. Here comes an important question. Then who is responsible for rotational motion? And the answer to that is torque. T-O-R-Q-U-E. So torque is a kind of effect. As of now, I'll call it as effect. When we deal in the chapter called as rotation motion, at that point I'll explain in detail. Is that point clear? So force is going to give you translatory motion. Whereas when you talk about rotational motion, like how I showed for the cat. So when you talk about rotational motion, what are the causes responsible for it? The answer to that is torque. T-O-R-Q-U-E. If I have to give you a simple example, let's say there is a screw. Okay, let's make it a simple point. Suppose I give you two pieces of wood. Okay, let's think like a carpenter. Okay? I give you two pieces of wood where I'm saying both the pieces are supposed to be attached with each other in the shape of L. Okay. What will I do? I'll take a Fevicol. I'll apply it at both the ends, at the edges, and start sticking it. That's one way. Okay, I'm lazy to apply Fevicol. What I will do is, I'll keep those two clamps like this, and I will take a nail and I'll place it on the top. To a nail, what you generally do, you take a hammer and you hit it. So when you're hitting the nail, so what are you doing? This is the hammer. When you're hitting it, the nail is actually having what kind of a motion? It is going in a straight line path. So what kind of a motion does it have? It has translatory motion. So to the nail, you're actually applying force. Whereas to the same two planks, I want to screw them. So I'll place a screw. Screw nobody goes and hits because screws have threadings, right? So for the screw to get inside, what you do is you take a screwdriver, you keep the screwdriver like this, and you tape it. So the screwdriver is actually applying torque. What did the hammer do? The hammer applied force. Screwdriver applied torque. And what did the Fevicol do? It just gave an adhesive force. It gave an adhesive force. It's chemical property. You know what is the adhesive property, right? Like how chemical, like how the particles just hold them in terms of ionic bond or whatever you call it, right? Covalent bond or whatever it is. They have a force between them, right? Which is not visualized by us. Whereas here Fevicol, what does it do? It has an adhesive force which is acting between two different substances, and because of that, it's. So you got your answer. So here, from this example, I want you to take only two important points. What is that? The work that the hammer did. The hammer applied force, and the screwdriver applied torque. Is it clear? So as of now, just have this word torque in mind. You need not think much of it. So going forward, whenever I say there is an object moving in a straight line, I'm indirectly telling you that the object is under the application of some force. So I'll not keep telling it every instant. That is why I'm stressing on this point again. Is it clear? So when it comes to this chapter 4, Newton's laws of motion, we don't generally discuss about torque, we are mainly concerned about force. Okay. And here, with respect to motion, I spoke about the cause being the force. Then what are these laws that we are trying to speak about? So here comes the answer. When you talk about Newton's laws of motion, right? So they are basically classified in three types. I'll not say classified. There were three laws that were proposed by Newton. What were they? We call them as the first law, obviously, first law, second law, and the third law. Right? So if we have so much of importance about these laws of motion, then obviously these laws are not going to speak about motion. Rather, they should speak more about the cause. Had it spoken something about motion, right? We have learned it in the previous two chapters. No, right? We need not wait till the fourth chapter. Actually, I'm sorry, it's chapter 5. But according to our syllabus, since the first chapter is deleted, it is chapter 4. Okay. So Newton's law. So we need not wait till now. So we have this first law, second law, and the third. So what does this first law speak about? First law speaks about a concept called as inertia. Right. And second law speaks about a parameter called as rate of change of linear momentum. Second law speaks about the rate of change of linear momentum. And the third law speaks about action, reaction, forces. Right? So we need to look at them in detail. Okay. Shall we? Can we proceed? So let's take this water bottle itself. Suppose I take this water bottle. Okay. If I keep it in my hand like this, you say that this water bottle is at rest. Right? It is at rest in terms of physics. Now, why is this bottle not able to move on its own? Because there should be some property associated with this bottle also. Why is this bottle not able to move on its own? So what do you call that property is? That's what is called as inertia. So every object in this world has a certain amount of inertia associated with it. But here comes an important question. What is inertia that I'm trying to talk about? So for that, let's try to have an understanding of what was the first law all along. So the first law was stated like this. Listen to this carefully. Every object in this universe, I repeat, every object in this universe continues to be in the state of rest or uniform motion. This is where you need to have a look. So he told that every object in this universe continues to be in the state of rest or in uniform motion unless and until an external force is applied on it. This external is an important because this bottle is made up of particles. If you go into the atomic level, it is made up of particles. How did I get this blue color? You took some spray paint, put on it. What is paint all about? Chemicals. Chemicals are obviously made up of atoms. Leave chemicals aside. Everything in this world is made up of atoms, right? So when you look at it, so those particles which are there inside, they are able to create a force and attract themselves to this surface. That is why this paint is intact. Or else what would have happened? As soon as you sprayed, had there been no adhesive force, what would have happened? This would have got chipped off. You would have seen the layer that is there inside. If I take and scratch it, I will be able to see it. Why am I able to see? Because I am creating a force against the adhesive force that is already existing. I am disturbing the equilibrium. Am I clear? Right, are you able to understand? So, these are all the forces which are happening within the system. Means this bottle is something which I'm trying to study about. So, this is called as the system according to Frick. So, if there are forces happening within the system due to the chemical properties of it, you call them as internal forces. It's internal with respect to the system. Whereas, if the same bottle I'm expected to move along the straight line, then I will start applying the force in this direction, right? So my left hand, the force that is applying is what is called as external force. And to stress on the important point, Newton's laws of motion doesn't speak anything about the internal force at all. It is mainly concerned only about the external forces. Is that clear? So before we speak about force, we need to understand what is inertia. Coming back to the basic again, this bottle couldn't move on its own because of the property that is associated with it, which is called as inertia. So basically, what is inertia? Inertia is the resistance offered by an object, some force that you try to apply. I repeat it, inertia is basically resistance offered by an object to the force that you apply. So it is not friction, don't get it confused. Okay, don't get confused here. So inertia is a property of the material. Friction has something to do with the contact surface. Just because I use the word resistance, I'll come to that. Don't write anything, listen. So I'll come to that. So what I'm saying is, if I say the resistance offered by an object to the force that you're trying to apply, you call that as inertia. I repeat it, do not get confused with friction, because friction acts between two surfaces which are in contact. So friction does not appear on the whole bottle, it appears only at the surface because this is in contact with my hand. Maybe if I rub it for longer duration, I can sense some heat also. Why is it happening? Because of friction. So I hope you're able to understand the difference. Now comes an important question. What property of the material is making it exhibit a property called as inertia? It is the mass of that particular object. So to put it in simple terms, if I have this bottle and I have this bottle, okay. So of course you are able to see the difference in the volume, right? And I'm not sure. I think they both are made up of same different materials also. So there is a difference in the density also occurring. Okay. So what is density to volume called as mass? So can I say that these two are definitely having different amount of masses? So if I try to place them on the same table and I apply the same amount of force on both the objects which are completely filled, which object among them do you think will start exhibiting more amount of resistance to my force? So I keep both the bottles on top of a table. I apply the same amount of force. If I apply 1 Newton force here, I'm applying 1 Newton force. Both are pushing force. Okay. Which one do you think will exhibit or will exert more amount of inertia to the force that I'm trying to apply? The bigger, because it has more mass. So inertia has something to do with mass. Inertia is not a measurable quantity. Inertia is only a comparative quantity. It means I can compare the inertia of two objects. Suppose someone comes and asks you, tell me what is the inertia of this. You cannot measure it numerically. You say inertia of this object compared to whom are you asking? Then I'll bring another body and say, compare the inertia among both and tell me. Then you will ask me a question, which one has more mass? So you will say this one. Then you will say that is the answer. The one which has greater mass has the greater inertia. Are you able to understand? So that is why the Newton's first law is also called as law of inertia. Okay, I hope every point is registered in your mind. With this, we are ready to take down the statement and the definitions. Please write it down. So let's look at the first law of Newton's first law of motion. What did it state? Every object, okay, I will add a point which has mass. Okay, every object which has mass will continue to be in the state of the rest or counterpart of rest is motion. So this is where we get confused. So if you write the statement as every object which has mass will continue to be in a state of rest or motion, the law is wrong. You need to stress on the point in the state of rest or uniform motion. Why is it so? I'll explain. So every object which has mass will continue to be in the state of rest or uniform motion till what point? Unless and until an external force is applied on it. And this law is also called as law of inertia. This law is also called as law of inertia. Now comes the next question of what is inertia? What is inertia? Inertia is the opposition. Inertia is the opposition offered by the object. Inertia is the opposition offered by the object whom the applied force. So opposition offered by the object, the applied force defined as inertia. And besides the inertia of an object, mass. So mass is the measure of inertia. So since I use the word measure of inertia, I repeat, you can never measure inertia, you can only compare it. So mass is the measure of inertia. Means inertia, I can say, is directly proportional to mass. So more is the mass, more is going to be the inertia. Right. The point that I need to answer here is, why did I use the word rest or uniform motion? What is the meaning of this word uniform motion? Let's come to it. Suppose this object is like this. Okay. So my hand is in this way. If I tilt my hand slightly, you're able to see it is moving. I didn't apply any force. I'm trying to tilt it and it is able to. Why is it happening? Because there is some gravitational force acting in this direction. Right. So if I hold it like this, it is going to be at rest. But as soon as I release it, it is going to fall in the downward direction. And why is it happening? Because of the gravitational force. This object has mass and there is something that is trying to pull the object. So what are we trying to say here? Every object continues to be in the state of rest. Okay. So here, if you see, is there no force acting on it? If I say there is no force acting on it, my answer is wrong. One is gravitational force is definitely acting, but my fingers are applying the sufficient amount of friction that is required to overcome this gravitational force so that the object as a whole is balanced. Okay. So here what has happened is, I repeat this point, if somebody puts a question, is there force acting on this object? The question is ambiguous. Are you trying to talk about individual forces or the net force? So, if you see the individual forces, they are not zero. Because gravitational force is there, friction is also there. They have some numerical value associated. But the sum of these two forces put together is zero. And this kind of a system where the forces get cancelled out are said to be balanced forces. Because this force, gravitational force, I'm not going to tell you the value at this point. So this gravitational force balanced by the value of the frictional force. So the sum of both the forces put together is zero. Now you can ask me, how can the sum of two forces be zero? Because force is a vector quantity. So one force is in downward direction the frictional force is acting in the upward direction. So though they have the same magnitude, since their directions are opposite, one will have positive sign, the other will have negative sign because of vector algebra, and they get cancelled. Is the point here? So they are able to stay unless and until I'm saying there is an external force that is applied on it. That external force is the one which is supposed to create unbalanced resistance. So from this, an important takeaway point here is an object will start moving only if the force that is applied on it is an unbalanced force. You cannot apply a balanced force on an object and say, no, it will not move. Right? I hope you understood from this example. Now the question is, I use the word state of rest. If I keep it like this is at the state of rest. So here also two things are happening. One is, if I move my hand like this, it is ready to fall down. See, it is ready to fall, but my hand is only stopping it. So I keep it here. So there is a gravitational force acting in this direction, and there is a reaction force offered by my hand. After Newton's third law, you will understand. So there is a force applied in the upward direction such that the sum of these two forces, the vector sum of these two forces will give you a zero. So this object is going to be at the state of rest even if you come after 10 years, it is in this kind of a scenario. If nobody disturbs it, it is going to be here only. Okay, so that is what they mentioned. It continues to be the state of rest. Or what do I mean by uniform motion? Uniform motion means if this object is given a velocity, let's say I've given it a velocity. Okay, I say you move and it started moving, right? It moved in such a way that its velocity at every instant of time is only 10 meters per second. So then this kind of a motion can be considered as uniform motion. What does uniform motion tell us? Velocity of the object is constant, and most importantly, acceleration is zero. So that is a point I want to stress again and again. So whenever we think of uniform motion, the first point that comes to our mind is everybody says velocity is constant. But the velocity being constant, what are you able to achieve? You are able to achieve the factor that the acceleration of the object is zero means its velocity or the magnitude of velocity is not changing with respect to time at all. Are you able to understand? So when I talk about the rest, right? When I talk about rest, what is zero? Velocity is zero. If velocity itself is zero, acceleration is zero. Similarly, when I talk about uniform motion, velocity is constant, but at the same time, acceleration is zero. So in both the scenario, if you take the intersection, what is common among both? Because the acceleration that is zero is common. Okay. Why I'm stressing on this word acceleration, you can understand its word. Is this point here? Right? So whatever point you want to make a note of, write it down. We'll proceed to the next one. Here. Let me proceed. Yeah. Awesome. So now we'll discuss about the next law, which is called as Newton's second. Right. So Newton's second law of motion. Before we try to understand this second law, one parameter that we are supposed to know is called as linear momentum. I'll just give it to you at side. So the concept we are going to discuss now is called as linear momentum, and linear momentum is represented by the symbol small p. It's represented by a small p. So linear momentum is a very simple concept. Okay. There's no derivation or anything. It is just a definition. If I have an object of mass, and if that object is given a velocity in a particular direction, I repeat it. Okay. If there is an object which has mass, assume, let's say that this is the car. Okay. So let's say my hand is the road. This object, this car has a mass associated with it. And let's say it is moving on this level road with the velocity v. Right? Then the physical quantity which gives you the product of the mass of this car with the speed of the object at that instant is what is called as linear momentum. So it is not a derivation, it is just a definition. So what is it? Any object with mass given a velocity, then the product of mass and velocity of the object is going to give you the linear momentum. Okay. So write it down. For any object of mass smaller and linear velocity v, we can define a physical quantity. We can define a physical quantity which is the product of mass and velocity. Product of mass and velocity, and that physical quantity is called as linear momentum. So linear momentum's mathematical definition is mass multiplied with velocity. I'm sure you have learned this in your lower grades. Right. So if you note certain important points here, linear momentum is a vector quantity. So linear momentum is a vector quantity. Reason being very simple. Mass is scalar, velocity is vector. So scalar multiplied with the vector will give you a vector. So linear momentum is a vector quantity. And what is going to be the SI unit for it? SI unit will be kilogram meter per second. So kilogram is the SI unit of mass. Meter per second is the unit of velocity. So kilogram meter per second is going to be the SI unit of linear momentum. Suppose you want to write the same thing in terms of CGS unit. How do you write it? As you write it as gram centimeter per second. So kilogram will be replaced with gram, meter will be replaced with centimeter, second is going to remain the same. So gram centimeter per second. It's going to be CGS unit of linear. Now we will see what does this Newton's second law of motion have to tell us. Right. So Newton's second law of motion mainly speaks about the rate, the time, the rate at which linear momentum is changing. Okay. Meaning, let's say there is a car. Okay. Generally, let's say when the car is in the parking lot, what is going to be the velocity of it? Obviously, zero. It's going to be at rest. Even if the engine is at start, nobody is going to accelerate it. No pedaling is going to be given. So let's say this car has started from rest. So what was its initial momentum? It had a mass which is a non-zero value. Mass of the car cannot be zero. Mass is still there. Then what was the velocity there? It was zero. So what was the initial momentum? Zero. As per this equation, mass into velocity. Now let's say you have taken this car from the parking lot, you have taken it in this direction. Right? You have taken it in this direction. So what is going to happen is this object having the mass its velocity changed from 0 to some other value. Had the velocity been 0 here also, then we cannot call about the relative motion. So what is needed for the object to move? Velocity, right? So it started from 0. As soon as you started accelerating, it is going to move in this direction. So its momentum changed from 0 to a non-zero value. Acceptable. Right? It has some velocity, let's say 10 km per hour, 15 km per hour, something is there. Right? So from 0 km per hour, it went to that value, which is a non-zero value. Right? So if I have to visualize the same thing in a diagrammatic format, let's say there's a car I'm trying to talk about, which has mass m. Okay. And initial velocity. So in the example part, I took it as 0 so that you can understand. So can I make the initial velocity as 0? So I'll make the initial velocity as 0. So what do I mean by initial velocity? This is the instant at which I started taking my measurements. So generally, initial doesn't mean, you can ask me, sir, car started from parking lot, you told me that it had 0 initial velocity. Maybe I didn't calculate it from that time. So once the car got started, right, let's say after it has attained some velocity, I started my stopwatch. So that will be the time which will be considered as initial velocity according to me. Are you able to understand? So if you mass in, the initial velocity is u at t is equal to 0. Let's say after some instance, the object has moved certain distance, right? So it has moved to a certain distance, so that here one important point to be noted. When can you change momentum? If you look at the physical quantity, you can say momentum can be literally changed when you change either mass and keep the velocity constant, or keep the mass constant and change the velocity, or you change both at the same time. It's up to you. So in the example that we are considering here, since I told about the car which is moving on a level, right? So car is obviously not going to lose its mass unless it loses some of its spare mass. Right? Something should fall from the car for its mass to change. The same people, everything is the same inside. Only thing that might occur is the petrol will get exhausted and that will come out as the smoke or whatever form it is going to come out. There will be a little bit decrease in the mass of the car accepted. But if you ignore that mass reduction, I can assume that the mass of the car is almost a constant. So here I want to stress on the point that when I'm trying to define this Newton's second law of motion, I'm trying to define it for an object whose mass is constant with respect to time. But what is changing? Velocity is changing. So if I say this velocity is v, and let's say this is taking place at some time t. So then we have yes. That's what I'm saying. Because there will not be much change. Okay. So mass is constant, initial velocity change to the final velocity. Now, if I am able to define something like this, change in momentum. If I put delta V, so how you read it, delta refers change, V refers momentum. So change in momentum is the final momentum minus the initial. Right? Change is always final minus initial. So what is going to be the final momentum according to this scenario? Mass multiplied with the velocity at that instant. It is going to be mv minus. Here, if I take the initial momentum, it is going to be m into u. So minus mu. So this is what is delta v. Accepted. Here, one more point I would like to consider is that the change in velocity of the object with respect to time is constant. Means I am saying that this object, I am of course able to observe that there is a change in speed taking place, no doubt in that. So whenever there is a change in speed taking place with respect to the object is either accelerating or decelerating. In this scenario, I am assuming that the object is accelerating constantly. Okay, I am assuming. So if there is a constant acceleration, if there is a constant acceleration, then if I define a parameter delta V by delta T, what will I get? I will get MP minus MU divided by delta T. So what is constant in the numerator? M is constant. So if I write M into P minus U divided by delta T, then I can write this as M into delta V divided by delta T. So what is the delta V by delta T? What is? This is what is called as the average acceleration. Then if you are able to define a parameter like this, then you call this as the external force. So that's what Newton's second law speaks to. So F external is equal to mass into acceleration. Maybe this is how you would have learned in your lower grades, but the matured way of explaining it is the external force is equal to rate of change of linear momentum. Statement, I'm writing it here. It's defined as the rate of change of linear momentum. That is, if you observe, external force is mathematically written as the product of mass and acceleration. And this is a very, very, very important equation, okay, which we'll be using to solve most of the problems. Most of the problems are solved using this. You need to know how to frame this equation. Because right hand side is only, left hand side you need to draw certain diagrams and understand how the forces are acting on it. That part will come soon. Okay. So as of now, we discussed about the Newton's first law of motion and Newton's second law of motion. So I hope it's clear. So those who are online, is it clear?
Yes, sir.
Yes, sir.
Shall I proceed? Right. So the next law which we are going to define is. So the next law which we are going to define is Newton's third law of motion. This is very, very, very simple. Right. So I discussed about this bottle. So if you observe this bottle, there was a force acting in the downward direction. You call it as the gravitational force. Right. So I will tell you the magnitude of gravitational force in the downward direction, friction in the upward direction. So if I call one of the forces as action, okay, then the force which is trying to oppose the action will become the reaction. So if you see, every action has an equal and opposite reaction. Are you able to understand? So every action, so gravitational force is acting in the downward direction has an equal. Why did I say equal? Because my system is at equilibrium. This term equilibrium is new to you. I'll explain it to you. Don't worry. But as of now, understand equilibrium means it is balanced. As of now, it is not moving. Okay, have it like that. So every action has an equal and opposite. Why did I say opposite? Because my fingers are applying the force in the upward direction to opposite. I'm able to sense it actually. Because water is filled in it. See, it's not getting balanced. It's toppling actually. Right. So every action has an equal and opposite reaction is what the statement of Newton's third law of motion. Right? The action has an equal and opposite reaction. Is this point clear? Since I use the word action and reaction, let me tell you some of the scenarios that are possible. Suppose I consider a table on top of which, let's say you place the on the top of a table, let's say you place the right. So what is the book experiencing? If I take my hand, okay, this hand is the table. If I move my hand, what is going to happen? Obviously, it will fall down. Right. So this is experiencing an action in the downward direction. So what is the action it is experiencing? So since I call the action is acting in the downward direction and which is a vector quantity, am I allowed to draw something like this? Right. Arrow mark. I'm saying there is a force acting in the downward direction, vector quantity in the downward direction. And I'll try to give a value to it. So my Newton's second law states F is equal to m into A. So let's say this object has mass m associated with it. So had this table not existed, what would have been the acceleration with which it would have started traveling in the downward direction? That is g, right? So I know that F is equal to m into A. So I'll replace this acceleration with acceleration due to gravity. So if I write this as mg, then this F is equal to mg is what is called as the gravitational force or weight of the object, which we'll slowly discuss. Okay. In this scenario, am I allowed to use? So F is equal to m into A. So mass of the object is m and the acceleration of the object is g. Right. So m into g. What did I say? This is also called as gravitational force or weight of the object. Okay. So if I say weight is the action exerted by the object on the table, then why will the table become? Right. It has to either give up or it try to oppose. When will it start giving up? When it is a weak. It starts breaking. Are you able to understand? If I take a very thin wood and try to keep a big, let's say I try to keep 150 kilograms or something on top of mass on top of it, what will happen? It might not be able to withstand, it will break. So what is the table doing here? It is exerting an opposite force in the upward direction, so that the whole system is at some scenario like this. So mg is acting in downward direction. The force exerted by the table on the book is called as the reaction. So if I write this reaction as R, then this reaction according to physics is called as normal. So this is what we call it as normal force. What is normal basically? Normal, it's perpendicular. So the force which is acting perpendicular to the surface is one of the reaction forces we are going to discuss in this chapter. Are you able to understand? So if you observe, I'm trying to combine many laws here. So I'm discussing about Newton's third law, but I took the help from Newton's second law, and here I wrote something else where I'm saying that is Newton's third law, because I'm going to connect everything at the end. Try to understand. Is it clear? So I hope there is no confusion in this one. You clear? Suppose I tilt the table like this. Okay. Suppose I'm tilting the table and I place an object of mass m here. Then what will happen is this object, whether I keep it like this or like this, it will experience force only the vertical direction. Okay. So what is going to happen? If this table was not there, it would have fallen down in the same direction. Don't get confused here. Don't think that it is going to go in this direction. It is going in that direction because of some component of this mg getting divided. Are you able to understand what I'm trying to say? So it will still have the ability to travel in the downward direction. Means if I move the staple, it will not go like this and fall. It will fall exactly in the downward direction. It will fall in the downward direction. So it will fall in this direction. But the reaction force exerted by the table on this block is going to be, on this book is going to be normal to it. So you're able to understand the difference between pure and so n is generally a simple use for normal. Are you able to understand the difference between this and this? Is it clear? So what is the difference? So here mg is completely balanced by the normal force, but here mg is not completely balanced. Why am I saying here action and reaction will not be the same? Now read the statement again. Every action has an equal in terms of magnitude and opposite in terms of direction. So if mg is acting in this direction, normal is acting in this direction. So for it to get balanced, normal should have been in this direction. Means our job is not at over here. We need to resolve this mg into different components and then solve it. So about which as of now will not worry. Just trying to explain how the different kinds of reaction forces can exist. Are you able to understand this point? Right? In a similar way. Let us say there is a circular object which is kept there is a circular object which is kept like this. Let's say this also has some mass. Yeah. Then what will happen? Mg will be in the downward direction. Right? Then how the normal force is going to exist. So this is one surface of contact. This is another surface of contact. Right? So the number of surfaces in contact with which the object is will be equal to the number of normal forces. So this will exert a normal force. Normal force perpendicular to itself. You can call that as N1. Then there will be a normal force which is acting perpendicular here also. You will call this as N. This is point here. Right. So here N1 might be equal to N2 or they might not be equal. We don't know unless we have the mathematical parameters. And I need to know different values associated with it. Again, I repeat, here the context is to explain the different kinds of reactions. Okay. You know, clear? Clear or not? Right? Now, I will try to connect all the laws. So first law, what did I speak about? Every object will continue to be in the state of rest or in uniform motion unless and until there is an external force applied. Right? So I told you state of rest means velocity is zero, acceleration is zero. Uniform motion means velocity is constant, acceleration is zero. Means the object is not moving at all. Means the object is moving, but it is moving with the uniform velocity. Next. So since I told acceleration in both the scenarios was zero, if I take that acceleration is equal to zero and put it here, what will happen? External force is zero. So what is Newton's second law state? F external is equal to F into A. If the acceleration of the object is zero, it can happen under two scenarios. What are they? One is when the object is at rest or when the object is in uniform motion. In both those scenarios, F external is zero. Then what can you say? That the object is either at rest or in uniform motion. is it justifying the Newton's first law of motion? Because all the three laws are proposed by him, he cannot contradict themselves. Is that right? So these two are stated and valid by the second law as well. And what is the third law speaking about? Every action has an equal and opposite reaction. So if every action has equal and opposite reaction, then the sum of all external forces will be equal to zero. So sigma is used for sum. If external is equal to zero. Are you an acceptance? Right? So in all the three scenarios observed, it is clearly stating that if the external force acting on the object is zero, the object has to either be in the state of rest or uniform motion. That point clear? That is why, if you see, whenever you want to experiment whether the object is moving or not, whether my force has succeeded or not, the first thing that you need to check is whether the object is experiencing acceleration. So from this I can conclude, wherever acceleration is zero, velocity is zero or velocity is uniform, but most importantly, force is zero. Are you able to understand the point? Right. So this is what the grammar of physics says. So this is what we need to study. Repeating it again. If in a question, they will not say the object is having a uniform motion. If at all they want to make it tough, they will say that the object is not accelerating. Then your mind should start asking what questions. So when they told it is not accelerating, then you need to put some questions. Are they trying to say that the object is at rest? Or are they trying to say that the object is in uniform motion? Or are they trying to say that the force acting on the object is zero? So these are the three questions which are pertaining to the acceleration constant. Is that point clear? Right? So only if these basics are clear, we will be able to solve some problems. Okay. So make a note of whatever I told you, write it down in your notebooks. What did I tell you about acceleration? Acceleration is zero means, what can you say? Object is either at rest or in uniform motion, or most importantly, force is zero. What force am I trying to talk about? External unbalanced force. Okay. Okay. 7.5. So just two problems. Simple problems. The kind of equilibrium is called as dynamic equilibrium. Now you'll see this. That's why I told you I didn't step much into equilibrium. When I come to the concept, actually the first set of problems that I designed are basically only on linear momentum and Newton's second law, but I try to compare everything with each. Okay. So let's try this. A car of mass 100 kilograms is moving with a velocity of 10 meters per second and is acted upon by a forward force of 1000 Newton due to engine and a retarding force of 500 Newton due to friction. What will be its velocity after 10 seconds? First, let's collect the data. Given parameters are mass, which is 1000 kilogram, initial velocity is 10 meter per second, force in the forward direction is 1000 Newton, force in the backward direction is 500 Newton. What will be its velocity after time is equal to 10 seconds? So tell me one thing. What's the net force acting on the object? Net force will be 1000 in the rightward direction minus 500 acting in the leftward direction. So don't get confused there. I did use the vector symbol here. 1000, I am saying this 1000 is pertaining to the forward direction and this 500 is pertaining to the reverse direction. So this is going to be equal to 500 Newton, and this 500 Newton is what is responsible for the motion of the object. So according to Newton's second law, can I say that the external force is equal to mass of the object into acceleration? So the external force is 500 is equal to, what is the mass of the object here? 1000 into acceleration. Can I write it as v minus u divided by t? So if you observe, it cancels. 1 by 2 is equal to v is what we need to find. V minus 10 divided by how much time? Since are speaking about 10 seconds. So which implies v will be equal to 15 meter per second. Means after 10 seconds, the object which started with 10 meter per second have started attaining a velocity of 15 meter per second. Is this point clear? Last one. So a bullet of mass 0.04 kilogram moving with a speed of 90 meter per second enters the heavy wooden block and is stopped after a distance of 60 centimeters. What is the average resistance force exerted by the block on the bullet? So you see there is a wooden block. If there is a bullet which has a mass of 0.04 kilogram, okay, and it is traveling with a speed of 90 meter per second, right? So when it has entered the wooden block, right, after it has got gears, it is able to travel a distance of 60 centimeters. And at this point, it is coming to rest. So at this point, the velocity of the object is 0. So by the time it started entering in this distance of 60 centimeters, it started experiencing a resistance. And that value is what they are resisting. So calculate the same logic. F is equal to mass to acceleration. So the F external is what we need to calculate, that is the resistance force is equal to mass of the object which is experiencing the resistance force is 0.04 because it is a bullet. So bullet is the one which is experiencing the resistance. In acceleration, I can write it as v minus u divided by t. Right? So 0.04 into the other way of writing this, we know that v square minus u square is equal to 2s. Reason why I am using this is because they are given distance, they are given time. So what I can do is, I can write acceleration is equal to v square minus u square divided by 2s. Right? So in this problem, what I can do, instead of using v minus u divided by t as the acceleration, I can use v square minus u square divided by 2s as the acceleration. So the final velocity of the bullet is going to be 0. So 0 square minus U is 90, so 90 square divided by 2 into the distance traveled by the object is going to be 60 centimeter. So 60 into 10 power minus 2 meter. So it's going to be 0.02. So 0.0 into 81 into 100 divided by 60 into 10 power minus 2. So this and this will get cancelled times. So 0.02 into 100 is 2. So 2 into 81, or I'll make it as 30. This will go 9 times, this will go 10 times. So 900 divided by 10 is going to be 19 Newton. So the resistive force that acted on the object was 19 Newton. Is it clear? Okay. So if it is all these concepts, tomorrow we'll discuss few more important things like impulse, then any other discuss. Clear? Those who are online will wind up this.
Thank you, sir.
Thank you, sir.